Okay, let's move on to lecture 3 of the first law of thermodynamics, right? So before we begin the lecture proper, let's just go through the exit pass 2 that you should have completed after the last lecture. Okay, so let's look at the first question. Okay, so first question, we have a fixed mass of gas that slowly releases 1,500 joules of heat and as a result contracts slowly at a constant pressure of 2 times 10 power 4 Pascal from a volume of 0.50 meter cube to a volume of 0.025 meter cube. What is the effect on the internal energy of the gas? Okay, so you're given the fact that it's releasing 1,500 joules of heat, so that is your Q out, and then also you have a change in volume at a constant pressure, so there's also some work done work done on the gas. Okay, so let's look at this. Since compression, positive work is done on the gas, and we can work out this value just by multiplying P times delta V, and you get 500 joules. Okay, then after this, you can just apply your first law, delta U equals to Q in plus W in. Because Q in is heat supplied to gas, but now heat is being lost, so I need to sub in as negative 1005 plus 500, so I get negative 1000 joules. So answer is C, decreases by 1000 joules. Right. Next, how would the internal energy of a fixed amount of ideal gas change if it's cooled at constant volume? Okay, and second one is when work is done on it at constant pressure. Okay, so first one, case one, because it's cooled at a constant volume. Okay, so your basically what we're looking for here, we can ignore the constant volume part because it's being cooled, right? So your delta T is less than 0, the temperature is decreasing. So if temperature is decreasing, the internal energy will also decrease as well. So delta U is less than 0. Okay. Next, case 2, work done on it at constant pressure. Okay, so if I do work on it at constant pressure, my work on is more than 0. And assuming that there's no supply of heat or loss of heat, delta U is more than 0 as a result. So answer here is decrease, increase, option C. Alright. Okay, next you have 100 grams of a liquid, currently volume is 100 cm3, evaporating at a constant pressure of 100 kilopascal to vapor of volume 0.167 meter cube. Assuming that the latent heat of vaporization of the liquid is 2.26 megajoules per kg, and the vapor behaves as ideal gas, which one of the following best describes the system? Okay, remember there are two things happening here. One is that the gas is the substance is expanding against atmosphere, so it's doing work against the atmosphere. So positive work should be done by the system. Alright. Then remember to do boiling, you have to supply energy into the system. So that's using the latent heat of vaporization. So first thing first, we can work out what's the work done by the system. So since it's expansion, work done by system is positive. So I can do work done by and just take the pressure, 100 times 10 power 3 Pascal. Then find the change in volume. Okay, 0.167 minus 100 cm cube divided by 100 cube to convert to meters cube. So I have 16.7 kilojoules. Okay, then Q in will be the mass of the sample multiplied by specific latent heat of vaporization. Right, so that's 2.26 times 10 power 5 joules. I just need to add up these two values. But remember, this is W by is positive, so W on is a negative value. Alright, so make sure you sub as negative value, and you get 209 kilojoules. Okay, so actually you can solve this by one step. If once you work out W by, you see that 16.7 joules, right? 16.7 kilojoules, right? There's only one answer that satisfies it, so that's option B. Sorry, bad cough. Okay, so let's move on to the next part. We're gonna go a lot deeper into the pressure volume graph. Okay, we're gonna talk about 5 different processes here. Okay, isobaric, which is basically done at constant pressure. You have isochoric or isovolumetric. The word iso basically means the same. Okay, so basically this one, the first one, isobaric constant pressure, isovolumetric constant volume, isothermal constant temperature, and we have adiabatic and isocyclic. Right? So let's look at each of these processes. How would they look like on the PV diagram? Okay, First, we have isobaric. This is the one that we're most familiar with. Okay, pressure change at constant volume. Alright, so this is how you represent it on the PV graph. Okay, so point A to point B. This shift is taking place at the pressure of P1 and it goes from V1 to V2. Okay, so and then if you do the steps here, okay, because P1V2 is larger than P1V1, that means the temperature at point B will be definitely higher than temperature at point A. Okay, so basically if you do an isobaric movement, right, there will definitely be temperature change. Okay, so I can work out the work done by, basically it's the area under the graph. If I want to find work done on, I take the negative area under the graph here. Of course, if you go from B to A, these two values would basically reverse itself lah, right? Okay, so this isobaric process. Okay, isobaric process is quite straightforward because you can see, oh, area under the graph, you just need to find the shape of the rectangle. Quite clear cut for this one. Okay, next let's move on to isochoric or isovolumetric. Okay, so pressure change at constant volume. Okay, so this is how it looks like on the graph. Point A to point B, constant volume of V1, but going from pressure P1 to P2. Okay, so since now P1 V1 is larger than P2 V1, we know that TA will be larger than TB. So definitely there'll be a temperature change as well. Okay, but since there's no volume change, work done by the gas or on the gas is 0. That means if you think about it, right, this change here, this change in temperature is brought about by heat supply or heat loss to the system, right? So WY equals to 0, W on is also 0. Okay, but delta U is not 0. In this case, delta U is a negative value. That means my Q in will also be a negative value as well. Okay, you can write out the equation. You can see very clearly once you have done that. Alright. Okay, next you have pressure change at constant temperature. Sorry, I have to pause the slides for a while to shift it slightly to the left hand side because my big fat head was blocking your screen. Alright, so isothermal, pressure and volume change at constant temperature. Alright, so this is how it looks like. Okay, let's look at this. This is how it looks like. Okay, so basically I go from A to B. A has a value of P1 V1, B has a value of P2 V2. Okay, I find points along the isotherm, along the in this space that has the same value of PV. Okay, all points along this path have the same temperature. Okay, so basically I'm trying to find P1 V1 equals to P2 V2. That means if I take any point along this line here, okay, I take the values of PV, it should be equals to the one for A and B. Okay, along this line, all of them have the same temperature. Alright, so all points along the red line has the same temperature. If you need to find work done for this case, against the area under the graph. Alright, so again, because there's no temperature change, delta U is 0. Okay, moving on. Okay, isotherms. Okay, what are isotherms? So just now we have looked at how this line here represents points with the same temperature. Alright, so right now, we can draw multiple lines to represent different temperatures. Okay, it can be drawn like this. Alright, and you can see that the further out I go, the larger the temperature will be, the higher the temperature will be. So if let's say I move my cursor along this horizontal line here, for the same value of P, the volume value will get larger and larger. That means it corresponds to a higher temperature. Okay, so basically these lines will not intersect one another, because if you think about it, right, if let's say you have T4 and T3 lines intersecting, right, that means there will be a point where the temperature is supposed to be the same, but that cannot be the case here. Alright, so the further out you go, the higher temperature. Okay, there's no limit to how many lines to draw. It depends on what you need. Usually when we are doing questions, right, we don't draw any of the isotherm lines. Okay, because isotherm lines are basically just to help you see whether they are at a particular, whether 2 points on the PV graph are they on the same temperature or not, right? So as long as your temperature is slightly different, let's say I pick a value that is between T1 and T2, I could draw a line in the middle. I could keep on dividing this and just keep on drawing as many lines as I need to. Okay, depends on how much you want to zoom in, how much you want to slice out the whole section. Alright, so basically isotherms, yes, if you move along an isotherm, you will have no change in temperature. That means you have no change in your U. If you go down to a lower isotherm, you have loss in temperature. That means your delta U is a negative value. If you go higher up, your delta U is a positive value. Right? So quite straightforward for this one. Okay, we look at adiabatic. Okay, adiabatic is a very interesting scenario. Okay, if you read this, pressure and volume change without heat supplied or lost from the system. That means here, my Q is 0. Okay, I'm not allowing heat to enter the system. I'm not allowing heat to exit from the system. Okay, how do I do that? Okay, like I said, you can either put some insulation. For example, you don't want the system to cool down its own, right? You put it into a vacuum flask so that heat doesn't escape. What else could you do? You could be supplying the same amount of heat as the amount of heat that's coming out on its own. Okay, that's one way. Or you can just do it very quickly. That means you do this setup, you do the change at a very fast rate, so there's no change in your there's no heat supply or heat loss from the system. Okay, same thing, you can still find work done. Okay, so let's show you how the movement can take place. Okay, so I can go from A to B, the red color line. Okay, if this is the case, right, let's look at how we can analyze this one first. Okay, so from A to B, because the gas has expanded as it moves from A to B, higher volume, the work done on the gas is less than 0. Okay, because positive work is done by the gas, therefore negative work is done on the gas. Alright, and since Q is 0, delta U will therefore be 0, because remember delta U is W on plus Q in. Okay, since W on is less than 0 and Q is equal to 0, delta U has to be less than 0. That means the temperature is decreasing. Okay, next we can show you one more. Right, we can go from C to D. Alright, C to D, you probably can see that right now this gas is being compressed. Okay, it goes from point C to point D, a decrease in volume. This will mean that C to D, negative work is done by the gas. That means positive work is done on the gas. W on is more than 0. And once you have that, you have C, since Q is equal to 0, delta U therefore must be more than 0. Temperature is increasing. Okay, one way to recognize adiabatic curves is usually steeper than isotherms, but it's not a very good comparison, because if you don't see isotherms, you can't really tell that this red and yellow lines are adiabatic processes. Okay, so it's very dangerous to assume it. Okay, but I think in the tutorial you will see some questions like that. Right. Alright, so this is adiabatic processes. Okay, this is the most challenging one, I would say, but actually just recognize that Q is 0 for this. No heat loss, no heat supplied to the system. Alright, let's move on. Okay, cyclic process. Okay, cyclic process, let me just show you on the diagram first. I start from point A and then I do a series of processes. Okay, A to B, B to C, and back to A. Okay, so this system goes from A to B, and then B to C, and then C to A. Okay, so right now, I undergo a series of changes and returns to its starting pressure and volume. Okay, because I start and end off at the same point, the P and V value is the same. And there's no change in temperature, and therefore no change in delta U equals to 0 over the full cycle. But for each of the process, A to B, or B to C, or C to A, there could be changes in delta U. Okay, there could be changes in your internal energy depending on how it is done. Alright, and of course, if I want to find the work done, you can see that, okay, if you go from A to B, the work done is kind of under here. See where my mouse is moving. Okay, and then from B to C, the work done is under here. And then from C to A, the work done is under here. So basically, I'm looking at this particular area here. Okay. Later you can see how you can calculate this area. You're not expected to calculate for such a complex shape. Alright. Okay, so if you have a summary, delta U from A to B, because I'm moving from T3 to T2, lower isotherm, there's a change in my temperature, so delta U AB is less than 0. B to C, moving along isotherm, delta U BC is equal to 0. C to A is moving up to a higher isotherm, so delta U is more than 0. But this 3 add up should give you 0. Alright, because it's a cyclic process. So that's how cyclic processes will work. Alright, this is very convenient thing to use when we are doing our calculations later. Right, so yes, delta U for A, B, C, A is equal to 0. Alright, so let's look at this example 9. Gas undergoes a cycle of changes from A to B to C to D to A, as shown in the figure above. Determine the net work done on the gas. Alright, so let's start from A to B first. Okay, A to B, basically the work done is this area here. And because the gas is being compressed, okay, contraction or compression, positive work is done on the gas. We can do this calculation very easily. We just take the change in volume multiplied by the pressure. Okay, so you get 20 joules. Alright, then there are two other processes, B to C and D to A. They are isovolumetric process, no change in volume, no work done. Alright, then moving on, we can look at now C to D. Okay, for C to D, the work done is under C to D. Okay, because it's expansion, negative work is done on the gas. Alright, and you get W on of negative 40 joules. Alright, so this is the net work done by the gas. Alright, I basically take this big triangle, big rectangle minus of the smaller one at the bottom here. Okay, I get this one that's enclosed. Alright, and you can see that here the net work done is a negative 20 joules. Okay, because remember this big rectangle is negative work done on the gas. Okay, because the gas is expanding. This small rectangle is positive work done on the gas. So in this case, this is negative 20 joules. Okay, so what you can see from here, let's say you have a simple set like this, right? If you have a clockwise rectangle, right, your work done on the gas is a negative value. Okay, if it's an anti-clockwise rectangle, it is a positive value. Alright, so this is one way you can quickly check your answer as well. Okay, so we look at example 9. Example 9, now we start to move on to the very fun part. Okay, to me it's fun, the fun part of this chapter. Alright, basically, one of the most common questions you have is that you have a table for each of process. Then I'll give you a table of this delta U, Q in, and W on. You're supposed to complete all the values there. Alright, and they give you some starter values to guide you along. Okay, so let's look at what we can do to fill up the rest of the values first. Previously, we have done some calculations so we can fill up the values up. Okay, so first step first, fill in the W on values that were calculated earlier. So A to B is a compression, so it's a positive work done. C to D is expansion, negative work done. B to C and D to A, constant volume, no work done at all, so 0. Okay, and you can sum up the last column, that's fine. Alright, and what else do we know? Okay, we know that because this is a cyclic process, A, B, C, D, A, overall the delta U should be 0. So this whole column here, all the delta U's when add up should give you 0. Alright, okay, so let's see what else we can fill up for this one here. Okay, we have already completed some of the rows. You can see that, the moment you only have one blank left, it's very easy to fill up. Alright, so first thing first, using the first law, I can fill up some of the values for A to B. So this is basically negative 50 because negative 50 plus 20 should give you negative 30. So I can see for B to C, I also can fill this up. 15 plus 0 should give me 15. Okay, and once you have this, you can also fill up this one as well. Okay, but let's see what I do next. Yeah, C to D first. Okay, so 100 plus negative 40 gives me 60. Okay, right now I have two blanks here, but so I can't really work this out. But if I look at this column here, I only have one missing value. Okay, so remember all these values add up should give me 1, 2, 3, 4 values add up should give me 0. So negative 30 plus 15, that will give me negative 15 plus 60 will give me 45. And then that means this one should be negative 45. So sum of all the delta U should give me 0. So that means delta U for DA is negative 45. And once you have that, you can fill in Q in. Okay, that's negative 45 as well. And then you can sum out the Q in if you want to, and then you should get 20, right? So yes, this is how you complete a table like this, right? So basically you find there is no fixed pattern that you need to, basically you're just trying to find out as many blanks as you can. Start from the simplest and just fill up as many as you can. Alright. Okay, example 10. Example 10 is, I think it's 10, 11 the longest examples. Okay, at 27 degrees Celsius and 1.0 times 10 power 5 Pascal, an ideal gas has a volume of 0.040 meter cube. It is heated at constant pressure until its volume increases to 0.050 meter cube. Determine the work done by the gas, determine new temperature of the gas in degrees Celsius, determine change in energy of the gas, determine total heat supplied to the gas. Okay, let's take this one by one. Work done by the gas, I think it's quite straightforward. We have constant pressure and then we have volume. Okay, but we don't have the final volume. So let's see what we can do. Sorry, we don't have the initial volume. Okay, but we know initial temperature, we know initial pressure. What else do we know? Oh yeah, we actually have the volume here. So we can just do P times delta V. Okay, so if we do it this way, yep, P times delta V just like that, we can work out the work done very easily. Okay, about 1000 joules. Work done by the gas is 1000 joules. Be careful the question here. Question is work done by the gas. So I keep it as 1000 joules. If I ask for work done on the gas, it's negative 1000 joules. Okay, new temperature of the gas in degrees Celsius. Okay, so we know a few things. Okay, since PV equals nRT for ideal gas. Question says it's an ideal gas ma. Alright, so this is what we can do. Okay, we can rearrange the equation a little bit. We form V over T equals to NR over P. Basically shift the P across and then shift the T across as well. Okay, so basically what this is doing is it's giving me a ratio of volume over temperature is equal to NR over P. And NR over P for this setup here, this is constant. N is number of moles, which is constant. R is universal gas constant, which is obviously a constant. P for this case, your pressure is constant. Alright, so basically you know therefore V over T is equals to a constant. So I can say V1 over T1 equals to V2 over T2. Okay, I sub in the values for the V1 and V2, 0.040 and 0.050. Okay, take note for this one, you need to use your thermodynamic temperature in terms of Kelvin. So add 273.15 to convert it to Kelvin. 27 plus 273.15 and equals to theta plus 273.15. And once you have done that, your theta is 102 degrees Celsius. Alright, so this one is a bit tricky because you need to work with this equation here. So some of you might not be very familiar with it for now. Okay, but with practice, I think it's okay. Normally when let's say I forget how to do these questions for this topic, I just play around with this equation. Try to I think for this chapter it's important to memorize most of the key equations, so it saves you a lot of time. Okay, next, for ideal gas, now you're supposed to find the change in internal energy of the gas. Okay, same thing for ideal gas. Your internal energy of the ideal gas is equals to 3 over 2 times P times V. Okay, this is from the previous chapter. So if I want to find change in ideal gas, okay, delta U is equals to 3 over 2 P times delta V because P is constant. So here what you're doing is that you are taking 3 over 2 PV1 minus 3 over 2 PV2. Okay, substitute in the values and then you should get the change in internal energy, which is 1500 joules. Alright. Okay, next, total heat supplied to the gas, because we know work done when we found out delta U already, right? So basically just sub in the values. Just now delta U was 1500 joules. Work done by the gas was positive 1000. So work done on the gas is negative 1000. Q in will therefore be 2500 joules. You realize that this system here, right? Because your gas is doing positive on the atmosphere, so it's losing energy. So if you don't supply heat into the system, right, your gas will definitely become cooler. Okay, so this is what you have, right? Okay, so moving on. Example 11. Okay, example 11 is quite tedious, but I think it's basically a combination of your chapters 11 and chapter 12. Okay, I have a cylinder that's fitted with a frictionless piston that contains 1 gram of ideal gas at a pressure of 1.01 times 10⁵ Pascal and at a temperature of 27 degrees Celsius. The following sequence of operations is performed on the gas. Gas is heated at constant pressure to 127 degrees Celsius, compressed at constant temperature to its original volume, cooled at constant volume to its original temperature. Okay, given that the molar mass of the gas is 18 grams per mole, the specific heat capacity of the gas at constant temperature is 650 joules per kg per Kelvin, and universal gas constant is 8.31 joules per Kelvin per mole. Okay, so there are a lot of things to take note of. Okay, so first thing first, let's illustrate the above processes on the PV diagram. Okay, they didn't give us the volume, but we just label as V1 and okay, this one should be V2. Okay, let me change it right now for you. Okay, let's go back to this one now. I've changed it to V2. So just take the V1 as the initial volume and V2 as the final volume. Okay, so first thing first, gas is heated at constant pressure to 127 degrees Celsius. So I start from V1. Okay, this is basically process A. Comes out straight away. So process A from V1 to V2 at 1.01 times 10 power 5 Pascal. And then from B, compress at constant temperature to its original volume. So basically compress, it goes back up to here. When you compress at constant temperature, you have to move along the isotherm. So you have to go up to here. Okay, up to this point here. And then cool at constant volume to its original temperature at this point over here. Okay, so A to B to C, this is a cyclic process. Rather, process A and process B and process C together, they form a cyclic process. Right, so this is the graph you need to draw. Okay, next, determine the work done by the gas in pushing the piston during process A. So process A, we are trying to find the work done under here. But we don't have volume, so we need to do some things to work out the volume first. Or maybe let's try some other methods and see how it goes. Okay, since this is an ideal gas, I know that PV equals nRT. I can rearrange this equation to find V equals to nRT over P. Alright, and that means if I sub in the value of all of them, I can find the volumes. Okay, so this is basically you can sub in, you can find you sub in N, R, and T1 over P. Okay, N is the number of moles, which you have 1 gram of sample, and the molar mass is 18 grams. So this is 1 over 18 of a mole. Okay, so multiply by R, multiply by the change in by your temperature, your thermodynamic temperature, divided by your pressure. So you get 1.372 times 10 negative 3 per meter cube. Do the same for V2, and then your nRT2 over P, summing the same thing, then you can get the same answer. Or you can combine the line to find delta V equals to nR over P times T2 minus T1. That works as well. I don't know why the fonts are a bit bigger here. I tried many ways to do it, but somehow the fonts are still different sizes. But I guess it's okay, not a big deal. Okay, then since this is an expansion, positive work is done by the gas. Okay, so you see that I will not care so much about substituting in the values in the correct order. I will first determine whether it's expansion or contraction. I will see whether I'm supposed to find work done by or work done on. Then with these two things in mind, I can decide whether I should take the positive value or negative value. Alright, so finding the work done is just basically pressure multiplied by change in the volume. And I get 46.2 joules. Okay. So, yep, this one is a bit more involved because you don't know the volume. You have to work. You need to use the ideal gas equation to find the volume first. Okay, determine the change in internal energy of process A. So since for ideal gas, because I remember ideal gas has no potential energy. Okay, so but I can use this equation. U equals to 3 over 2 nRT. So just sub in the values. Okay, so 3 over 2 times 1 over 18, number of moles 8.31 R. Difference in your thermodynamic temperature 127 minus 27. Actually here I'm not using thermodynamic. I think I'm using because it's a change, so the change is the same. Alright, if I use thermodynamic, I'll still get the same outcome. And doing this way, I get 69.3 joules. Alright, so I think you might be a bit confused where we are right now. Next, then you are, I think that's, determine the heat input to the cylinder process A. So since we work out the work done, which was work done by the gas, is positive 46.2. Delta U over here 69.3 joules. I can work out Q in. Q in is 116 joules. Okay. See now, because the gas is expanding, okay, the gas should be losing energy, but yet I'm still gaining energy. That means Q in must be larger than the magnitude of Q in must be larger than the magnitude of W on in order to get this value here. Okay. Right. Let's move on. Example 11 part E. Determine the change in the internal energy of the gas in process B. Okay, process B, basically there's no change in temperature. I think I should backtrack to show you where this one is. Let me find that slide for you. Go to slide. Yeah, this one over here. Right, process B is an isothermal reaction. So it's isothermal change. There's no change in your internal energy. Let's go to the next slide. I think it's this one. Okay. Yep. So change in the internal energy of the gas in process B. Since no change in temperature, delta U is 0, isotherm. Okay, next. Determine the heat extracted from the gas in process C. Okay. Process C, since the three processes are cyclic, okay, I can add up the delta U's, it should give me 0. Because I already know the delta U for A and I know delta U for B 0 as well, and I just need to find delta UC. Okay, so this is negative 69.3 joules for negative delta UC. And if you remember, delta process C is an volumetric change, no work done. Okay, since process C occurs at constant volume, work done on the gas is 0. So I can find the heat extracted from the system this way. Delta UC equals to Q in plus W on. Sub in the values again. Negative 69.3 equals to Q in plus 0. Therefore, Q in is equals to negative 69.3 joules. Okay, so because it's asking for the heat extracted, you need to give the positive answer. Remember, Q in is the heat supplied into the system, and you get a negative value. That means positive heat is being extracted from the system, right? Okay, let's look at, you can try exit pass 3 now. This is the last lecture actually. I should be going through, or some tutors will be going through the tutorial questions. But this one I'll record another video to show you the solution for exit pass 3. Alright, so please try these questions. Should take you, this one is a bit more involved. That should take about maybe 20 minutes or so to try the questions. Okay, if not, that's all. Thank you.